I'm going to be talking about some preliminary results on a project that Martin Dorn and I are working on, which is looking at the impact of changes in natural mortality at age on the performance of the current management strategy used for the Gulf of Alaska walleye pollock fishery. Martin Dorn is the stock assessment author. So management strategy evaluation is looking at simulation testing with feedback to determine how robust a management strategy is to various sources of error and uncertainty, including process and observation error, model misspecification, regime shifts, climate variability, ecosystem impacts, implementation error, and other influences. When we did this project previously with data through 2006, we looked at these first 5 types of error and uncertainty. So this is the Gulf of Alaska is up here, and the fisheries take place on the shelf and the slope up here. A walleye pollock occurs across the North Pacific, and even though there is a fairly large population in the Gulf of Alaska, here the population in the eastern Bering Sea is a order of magnitude higher. And the annual catches are usually between 50 and 100,000 metric tons. Last year, I think the total allowable catch was around 115,000 metric tons, and this year it's around 160,000 metric tons. So the current management strategy has been used since 2001. It consists of a statistical catch at age population dynamics model and a harvest control rule, and the stock is assessed annually. So the overfishing limit is based on F35% harvest control rule, which is the overfishing limit, and F35% is a proxy for FMSY. The harvest control rule for this stock has usually been F40%, but Martin Dorn adjusted this so that the decrease occurs around SB 40% instead of SB 40%, which is where the decrease occurs previously. Also, if the stock is ever assessed to be below SB 20%, directed fishing is stopped for stellar sea lion protection measures. So the previous results that we got for the MSE, basically there is an unintended precautionary bias in the stock assessment with respect to the operating model, a median bias of minus 10% for spawning biomass, median bias of 10% for fishing mortality, and a median bias of minus 10% for ADC, so that the stock assessment and harvest control rule are estimating an ADC that's about 10% less on average than the ADC for the true population given the harvest control rule. And so we show that the management strategy was robust to several sources of error and uncertainty. However, when we looked at including ecosystem impacts, we used 3 primary predators as fisheries, and that process did not work well, and those results were quite different from the other results that we got for management strategy evaluation. And so since then, I've been considering other ways, either directly or indirectly, to look at how changes in natural mortality at age might impact how well the management strategy performs. So why we wanted to take a look at this, here we have estimates of biomass for walleye pollock and 4 of its predators over the historical period. Walleye pollock peaked in the early 1980s, and then there was peak or reasonable half level of that in the early 1990s, late 1980s, and since then the stock has not gotten back up to that point. Pacific cod and Pacific halibuts have been fairly stable over the particular time. However, arrowtooth flounder have increased almost linearly over that period of time, which is of particular interest because of the diet data. This is diet data from one of the surveys. For 3 of the predators, we have arrowtooth flounder, Pacific halibut, and Pacific cod. This vertical line here indicates the 30-centimeter measurement. Fish smaller than 30 centimeters are predominantly ages 0, 1, and 2, and fish larger than that are ages 3 and above. So looking at the fish, the size of the walleye pollock consumed by arrowtooth flounder, it's predominantly ages 1 and 2, and with very few adults consumed, versus what Pacific cod and Pacific halibut consume. Pacific halibut also consumes some of the younger, smaller fish, but also a fair amount of adults, which is slightly different from Pacific cod, which eats some of the smaller, younger fish, but predominantly the adults. So the biggest concern here is that the age 1 and 2s might be significantly impacted by the changing biomass of arrowtooth flounder over the historical period, and what impact that might be having on the management strategy that aren't being taken into account right now. So the motivation of this work, is that in the last couple of years, Martin Doan has made a couple of changes to the stock assessment model. The main difference between the operating model and the stock assessment model is the age range. The operating model covers ages 1 through 15, and previously the stock assessment model covered ages 2 through 10, and now Martin has extended it to ages 1 through 10. There's also, he's included independent survey selectivity for age 1 fish, which kind of confounds actually trying to estimate or set a different fishing mortality or natural mortality for age 1 fish. So M is assumed to be 0.3 for all ages, and previously for the MSE work, I did a likelihood profile on H1M, and so we ended up with the result that M was 0.75 in the previous MSE analysis. And so I was curious to see how different values of M would actually be impacting the management strategy now, since we're assuming M for age 1 is 0.3. And we also see that arrowtooth flounder biomass is still increasing even over the more recent period. These are stock assessment biomass results from last year, and Pacific cod is still fairly stable, maybe decreasing over the historical period, versus arrowtooth flounder is still increasing, maybe not linearly, but it's still quite high level relative to where the pollock biomass is. And pollock biomass has also increased a bit during the more recent period, but still not up to even the levels of the late 1980s and early 1990s. So the scenarios that we looked at, we used a 30-year projection period, and I'm using for this analysis last year's stock assessment model and the data available to the stock assessment model. We projected 101 populations forward through this projection period, one based on the maximum likelihood estimate, and then 100 based on samples in the Bayesian posterior. So we looked at 4 different types of maximum value for M at age, 0.7 and 1 for age 1, and then including changes to age 2 and age 3 as well. For these 4 types of maximum values for M at age, we also looked at 3 patterns in changing M at age. So M, whichever for age 1, age 2, or age 3, increases linearly from 0.3 to the maximum value over the entire projection period. It increases linearly over the middle 10 years of the projection period, or there's a stepped increase from 0.3 to the maximum value in the middle of the projection period over 1 year. There were also 2 ways that I looked at generating future recruits, but as those didn't really impact the bias, even though they impacted the spawning biomass, I'm not going to talk about that very much. The performance measures that I'm going to be showing are what the true spawning biomass, as represented in the operating model, have been over the projection period. Percent relative error in spawning biomass, fishing mortality, and ABC. And interest to management, how often does overfishing occur, which is how often does the true fishing mortality is greater than the overfishing level of fishing mortality. So summary of the results for some of the simpler scenarios. For the base scenario, consistent with the previous results, we have a median bias of -15, -10% for spawning biomass, 10 to 15% in fishing mortality, and -15, -10% in ABC. Overfishing occurs over the entire projection period in any given year less than 5% of the time. You get similar results when maximum age 1M is 0.7, and still getting very little overfishing occurring. And for the 3 different patterns of changes in M at age over the projection period, there were very little differences between all three of those. There's a little bit of a difference in the results looking at maximum M at age 1M of 1. So we have an increase in bias for spawning biomass, decrease in bias in fishing mortality, an increase in bias in ABC, so that by the end of the projection period, the ABC calculated by the management strategy is on average the same as the true ABC in the operating model. And there's a maximum of less than 10% overfishing, so still a low level budget increase in overfishing. And there also is a slight difference among the 3 different patterns of how M at age changes over the projection period. So looking at one of the more extreme scenarios that we looked at, we can see more significant differences between M increasing linearly over the entire projection period versus M increasing more rapidly, either in the increasing over the 10 years in the middle of the projection period or the step increase. This is shown, the top row here is one of the methods that I use to generate future recruits, and the bottom row is the second method. And this, since the second method usually results in lower future recruits, that's why the biomass is lower for all of these. This is true spawning biomass is represented in the operating model. The column on the left is for ramp up over the entire projection period. The middle column is the ramp up over the middle 10 years of the projection period, and the right column is the step increase in the middle of the projection period over 1 year. So there's very gradual decrease in spawning biomass when the M&H is changing gradually. There's a little bit more of a steep decline when the decline in M occurs more rapidly, and the step increase, the decline is even more pronounced, and there's a lower level of biomass at the end of the projection period than there is for the more gradual increase in M. Looking at how bias has changed, bias increases for the gradual ramp up from about median value of about minus 15% to about minus 5% by the end of the projection period. However, for the more rapid increase, we increase from minus 15% to above 0%, so that the management strategy is estimating a slightly higher level of spawning biomass than actually is in the operating model. Looking at how this and some of the other impacts affect ABC, see that the bias in the early part of the projection period is minus 15%, and this increases to almost 10% by the end of the projection period. And this is not good in particular because this increase of bias being positive occurs in the middle of the projection period where M at age 1 is 0.65 and M at age 2 is 0.5. So that even here in the middle where there's been a gradual shift in M at H, we're starting to see issues of differences in ABC. And this is even more pronounced for the more rapid increase in M, where the bias at the end of the projection period is on average 20%. So that the management strategy is estimating an ABC that's 20% higher than that for the true population. Overfishing occurs for the more gradual ramp up by the end of the projection period about 10% of the time, and then for the more steep increase in M at age, about 25 to maximum about 30% of the time by the end of the projection period for the other two scenarios. Looking at the more even extreme scenario where M at age changes for ages 1, 2, and 3, we can see those differences that we saw for the previous scenario even more distinctly in these results. So the bias in spawning biomass goes from minus 15% to about 5% for the ramp up over the entire time period, versus the step increase, the bias results in about a median level of about 10%. Looking at how this impacts ABC, we get resulting ABC bias of 20% by the end of the projection period for the ramp up over the entire projection period, and a median bias of about 40% when ramping up over the shorter time period, so that the results are even more extreme than the previous scenario. And again, this starts occurring in the middle of the projection period, so that even for moderate increases in M at age, we're starting to see issues of the ABC being higher than it should be given the true state of the stock. Overfishing occurs in the latter part of the projection period, about 20% of the time for the ramp up over the entire projection period, and almost 50% of the time for more rapid increase in M at age, which is very concerning as well. So summary for these results, the current management strategy has an unintended precautionary bias, which matches the previous results that we had. The current management strategy can account for some changes in M depending on how rapid those changes are and how extreme those changes are. and the current management strategy is not robust to changes in M for any fish older than age 1. And so this has led to some discussions with Martin about how he actually would account for changing M, particularly for calculating the biological reference points and how to include those changes in M as well. That's it. Thank you. Any questions?